Okay, a long one. So the first four parts of the problem are just some algebra, right? And so you probably are okay with those? Yeah. Okay, so let me just comment very briefly on, let's say, the first one here. This is a nice fact about angle in the right half plane and how it relates to the rectangular coordinates y over x. And unfortunately, we have to be careful about, I mean, I can't just say that this is true everywhere, right? Because arctangent doesn't give you every possible value of theta. So this only works in the right half plane, right? Nevertheless, on the right half plane, you can take this formula for theta, take the appropriate partials, and you get that that's its gradient. And then for the upper half plane, well, this is a true statement about x and y and how they relate to theta. And seemingly coincidentally, the gradient happens to be the same, at least as a formula. But critically, this is only defined, well, I'm only defining this in the upper half plane, right? So for one thing, this doesn't make any sense if y is equal to 0. If y is equal to 0, this is garbage, right? And likewise here with this, I can't say anything about what happens if x is equal to 0. This is garbage. Okay, ditto, ditto. Okay. Okay, so these all have the same formula. Okay, and so they agree on the overlap. Do you see what I mean by they agree on the overlap? Okay. Okay. All right, so in fact, altogether I have a new vector field that is that formula defined everywhere. All right. Okay. Excuse me. I misspoke terribly. Defined on all of these half planes, but those don't cover everywhere. They cover everything except for the origin. I do want to draw a picture of that. So here's the plane. The right half plane is all of that. The upper half plane is all of this, etc., etc., and altogether that's going to include all the points except for the origin. Does that make sense? Okay. All right. Okay. All right. Direct computation, Green's operator is 0. You're okay with that one? Okay. So it's just a matter of taking this vector field. There's your Q, there's your P, dq dx minus dp dy. Okay. All right, we're halfway done. Okay. Starting off, x1 and x2 are both points in the right half plane. And C is any curve in that half plane from x1 to x2. Then this line integral gives the difference in the values of theta. All right, so you okay with this part, or do you want me to talk you through this part? Why don't I talk you through this part? Yeah, okay. Okay. Okay, well, they give us a big hint. Use the formula within the line integrals. It says right there. Right, so that means, here, let me write this down. Let's see, it's integral over C of f dot dx. Alright, well, we've got a point. Here's x1 and here's x2. And our curve is some path that goes from x1 to x2. And we're looking at the integral over this curve of f dot dx. Okay, fine. Well, now, wait a minute. Green's operator is 0. So I'm highly suspicious there's an anti-gradient. The function's only defined on the half plane. I mean, there's technically our theorems don't tell us there's an anti-gradient, but I think maybe there is. And in fact, check it out. We already know there is. Look at this. Theta 1, that function theta 1, is an anti-gradient because that function theta 1, its gradient is f on that half plane. Does that make sense? Mm-hmm. Okay, so we have an anti-gradient. It's theta. So I can cite the fundamental theorem of line integrals. This is theta of x2 minus theta of x1 as required. Is that good? Yeah. Okay. You doing okay as well?
That's just the answer.
Well, that's the answer to that part. Yep.
Yes, since this is the right half plane, would we use arctan of y over x?
Mm-hmm. Yeah, exactly. So where's my little thing? Here it is. So you have to use exactly this function because it's only this function that we know on that right half plane has this correct gradient. Yeah. Okay. All right. All right. So that was part 6. All right. Part 7. Suppose x1 and x3 are in the first and third quadrants, respectively. Did I do these? Okay, whatever. Okay. And C is any curve from x1 to x3 that goes through the second quadrant and then into the third quadrant. Okay, it doesn't touch the fourth. There's certain rules. All right, now there's a big. So again, the punchline is the line integral gives the difference between the values of theta at those 2 points. Okay. The hint is to choose some point x2 that's on the curve in the second quadrant. Let me draw the picture of what we're talking about here. Our new scenario, we've got x1 is there, and x3 is here. And our curve goes from there to there by way of the second quadrant, and it's not allowed to go anywhere over here. Right? Well, if it's not allowed to go through there, then it's got to look, I'm going to say loosely like what I've got here. And the hint then says, okay, pick some point x2 in there. Cool? All right. And then let's remind ourselves what the hint then says. The hint then says, use the, okay. Okay. All right. So let's take this curve into 2 chunks. First, let's think about that piece of curve. On that piece of curve, I'll call that C1. What's the integral on C1 of f dot dx? Well, on C1, very importantly, we are in the upper half plane, right? And in the upper half plane, our vector field is the gradient of theta 2. Is that cool? Yeah, because going back to our givens, on the upper half plane, our vector field is the gradient of theta 2. Okay, so the point is that that means this line integral, being as it is an integral of a gradient, gives me theta 2 of x2 minus theta 2 of x1. Okay, so the point is it gives me this angle. Right? It gives me that. All right. Now let's consider this other second half of the curve. So we'll call that C2. And the integral over C2 f dot dx. Well, now, I can't talk about theta 2 anymore. Right? Yeah, theta 3. Yeah, exactly. Theta 3 is perfectly well defined on this left half plane. So on this left half plane, on C2, we're talking about the gradient of theta 3. And so this line integral gives me, I'm just going to say theta here because, I had to define theta 2 and theta 3 separately because they're only defined in certain regions, but they're giving us the angles that we know we're talking about. So this is theta of x3 minus theta of x2, and that gives me this angle. Is that cool? You doing okay? Okay. Alrighty. Well, that was part. Which part? That was part 7. Okay. Making progress. All right. So part 8. Okay. So now we're going to start. Yeah.
These two together.
Oh yeah. Okay, no, you're right. I didn't quite finish there. You're very right. So yeah, so all together.
My problem was I didn't know if I should add them together.
Oh yeah. I'm sorry, I misunderstood. Okay, sure, cool. Come back to here. So the question was to find the line integral between of that line integral from x1 to x3. So in fact, I wanted to compute the line integral over the entire curve, and the line integral over that entire curve is, well, it's the line integral over C1 plus the line integral over C2, and so it's, that angle plus that angle, and therefore it's, that total angle there. Does it make sense? Okay. Cool. Okay. Okay, so are we okay to move on to 8?
But then do these cancel out since they're different?
Yeah, you get theta 3 minus theta 1. Yeah, okay, I keep spiking the football on the 2-yard line. We had this minus that, but they're the same actually. So the theta 2, so this theta, this theta 2 and where this, theta of x2 and this theta of x2 are the same because they both refer to, man, I knew I was going to hit that. Theta of x2 is that angle. So that angle is going in this direction. That direction is in the upper half plane. It's also in the left half plane. And so theta 2 and theta 3, they're the same value for that, for x2. Does that make sense? Yeah, it's good to be worried about that. Absolutely, but it is okay. Yeah. Okay, yeah, so those cancel, and so I get theta of x3 minus theta of x1. So it's the difference in the angles. It's that angle. Yep. Okay. Now let me just double check and make sure that is what we were supposed to show. Yeah, the difference between the values of theta at those 2 points. Okay. Okay. Part 8.
Is
All right.
part 8 just 0 since this?
Nah, that's the worry. Yeah, so let's take this one really slowly and carefully. We're going to start and end at a point in the first quadrant, going a counterclockwise loop around the origin. First quadrant, second quadrant, third quadrant, fourth quadrant. Okay. All right. Let's draw that picture. Okay, and I'm going to get rid of all this mess. Having learned this lesson. Oh, you know what? I can do this better than that. guess I could have just deleted everything and drawn that again. Okay, all right, so we're going to start here, and then it describes that we're going to go into the second quadrant, and then into the third quadrant, and then into the fourth quadrant, and then back to the first quadrant. Okay, so this is our curve. And so I'm going to argue as follows. If we want to compute the line integral over this curve, I can break that up into steps, and I'm going to draw some convenient guidelines here. And let's call this C1, and then we'll refer to that as C2, and then we'll refer to that as C3, and that's C4. So here's the thing. We've shown in a couple of examples that when you do a line integral of this special vector field f over one of these curves, you get the angle, right? The difference in the angle. So with the first curve, we're going to get that angle. With the second curve, we're going to get that angle. Now that's, I mean, bigger, right? I mean, we're adding more angle. And then with the third curve, we're going to get that angle. That's even bigger. I mean, this is, we're adding positive numbers here, right? And then over this curve, we get that angle. Now, these angles add up to 2 pi because we made a loop, right? So all together, all the way around, they add up to 2 pi. Now, what's weird is I can't say that this is the value of theta there minus the value of theta at exactly that same point, because that would be 0. This isn't 0. See what I'm saying? It's like, you know, if you're keeping track of theta as you go around, your little the change in theta has been increasing all the way around until, you know, you get to there, and so it's not 0. It is 2 pi. Make sense? So the problem is, you know, if you want to, here's another way to say it. You can't really define a function theta that's defined everywhere because of exactly this problem. If you want to talk about this function theta, whatever the value of theta is at that point, well, it keeps getting bigger and bigger as you move around, and it keeps getting bigger and bigger and bigger and bigger and bigger, and uh-oh. Right now it needs to be 2 pi bigger than it had been, even though it can't. You know what I mean? Yeah. So, yeah. Okay, now let me go back to the thing. What were we? Yeah, right. So what is the value of that line integral? Well, it's 2 pi. Okay. So, so why can't this be a gradient of some function? Well, if this were the gradient of some function, then we would be able to argue as follows. If f were hypothetically the gradient of some mystery function that I'm going to call m for mystery function, question mark, hypothetically if this were the case, then this line integral that we just computed would have to be the value of this mystery function at the ending point minus the value of this mystery function at the starting point, which is, I'm sorry, x1, which would have to be 0. But it's not. It's 2 pi, and that is not possible. So therefore, there is no mystery function. There is no anti-gradient for this thing. Does that make sense? Mm-hmm. Okay, now let me put the final, so like what was the point of this whole exercise, right? The point of this exercise is it would appear we have found a counterexample to one of our lifetime theorems, because we've got a vector field here. Got a vector field where Green's operator is 0 everywhere in the domain. The whole domain. The domain is the punctured plane. It doesn't include the origin, right? But everywhere in the domain, Green's operator is 0, and yet this function, this vector field, is not the gradient of any function. Seemingly a counterexample to our lifetime theorem. But then I go back to the lifetime theorem, and there is this really important, and again, the part of the purpose of this example is to give you a lengthy and hopefully hard to forget example of the importance of this condition, which I guess I'd put here. Yeah, okay. It's got to be defined on all of R2 or all of R3. And this is non-negotiable. This is a really big deal. This is not one of those things where it's like, well, just, it's true wherever it's defined, and it's fine. Does that make sense? You doing okay as well?
Yeah, so basically the problem we just did didn't work because it wasn't defined on the origin.
Yeah, that's right. I mean, well, it seemingly violated one of our rules, but in fact it didn't. This is not a counterexample to our theorem. This is just an example that doesn't satisfy the conditions of our theorem. And you're quite right. The condition that it failed to satisfy is that it's not defined at the origin. Yep. It failed to be defined everywhere. Defined and furthermore continuously differentiable.